So why don't you start off with maybe some opening remarks, and then I'll ask you a few questions, and then you get the tough questions.
Well, I think that after your opening remarks, it is smartest for me not to make any opening remarks to avoid risking damaging all the good things you said. But let's see. It's always good to have a pickup line, and mine was do you want to see my homework? Yeah, and you're right. We're married still. We have 2 beautiful kids. I have a perfect life, 2 great puppies, and I love my job, and she still enjoys my homework.
Well, if you want, I can ask you a few questions then.
Yes, please.
So, in my lifetime, I thought the biggest technology breakthrough was the transistor. Now, I'm older than you. Yeah. And it was pretty fundamental.
It's a big deal, yeah.
But should I rethink? Is AI now the biggest change in technology that has occurred in the last 76 years? To hint at my age.
Yeah. Well, first of all, the transistor was obviously a great invention, but what was the greatest capability that enabled was software. The ability for humans to express our ideas, algorithms, in a repeatable way, computationally repeatable way, is the breakthrough. What have we done? We dedicated our company in the last 31 years, to a new form of computing called accelerated computing. The idea is that general purpose computing is not ideal for every field of work. And we said, why don't we invent a new way of doing computation such that we can solve problems that general purpose computing is ill-equipped at solving. And what we have effectively done in a particular area of a domain of computation that is algorithmic in nature, that can be parallelized, we've taken the computational cost of computers to approximately 0. So what happens when you are able to take the marginal cost of something to approximately 0? We enabled a new way of doing software where it used to be written by humans. We now can use computers to write the software because the computational cost is approximately 0. And so you might as well let the computer go off and grind on just a massive amount of experience we call data, digital experience, human digital experience called data, and grind on it to find the relationships and patterns that, as a result, represents human knowledge. And that miracle happened about a decade and a half ago. We saw it coming, and we took the whole company and we shaped our computer, which was already driving the marginal cost of computing down to 0, and we pushed it into this whole domain. And as a result, in the last 10 years, we reduced the cost of computing by 1 million times. The cost of deep learning by 1 million times. And a lot of people said to me, but Jensen, if you reduce the cost of computing your cost by 1 million times, then people buy less of it. And it's exactly the opposite. We saw that if we could reduce the marginal cost of computing down to approximately 0, we might use it to do something insanely amazing. Large language models. To literally extract all of digital human knowledge from the internet and put it into a computer and let it go figure out what the knowledge is. That idea of scraping the entire internet and putting it in one computer and let the computer figure out what the program is an insane concept. But you wouldn't ever consider doing it unless the marginal cost of computing was 0. And so we made that breakthrough. And now we've enabled this new way of doing software. Imagine, for all the people that are still new to artificial intelligence, we've figured out how to use a computer to understand the meaning, not the pattern, but the meaning of almost all digital knowledge. And anything you can digitize, we can understand the meaning. So let me give you an example. Gene sequencing is digitizing genes. But now with large language models, we can go learn the meaning of that gene. Amino acids, we digitized, through mass spec, we digitized amino acids. Now we can understand from the amino acid sequence without a whole lot of work with cryo-EMs and things like that, we can go figure out what is the structure of the protein and what it does. What is its meaning? We can also do that on a fairly large scale pretty soon. We can understand what's the meaning of a cell. A whole bunch of genes that are connected together. And so this is, from a computer's perspective, no different than there's a whole page of words, and you asked it to, what is the meaning of it? Summarize. What did it say? Summarize it for me. What's the meaning? This is no different than a hard, big, huge, long page of genes. What's the meaning of that? Big, long page of proteins. What's the meaning of that? And so we're on the cusp of all this. This is the miracle of what happened. And so I would, it's a long-winded answer of saying, John, that you're absolutely right, that AI, which was enabled by this new form of computing we call accelerated computing that took 3 decades to do, is probably the single greatest invention of the technology industry. This will likely be the most important thing of the 21st century.
I agree with that. 21st century, but maybe not the 20th century, which was the transistor. It's got to be close. We'll let history decide.
That's right.
We'll let history decide. Could you look ahead? I take it that the GPU chip that is behind artificial intelligence right now is your H100, and I know you're introducing an H200. And I think I read that you plan to upgrade that each year. And so could you think ahead 5 years, March 2029, you're introducing the H700.
Right.
What will it allow us to do that we can't do now?
I'll go backwards, but let me first say something about the chip that John just described. As we say a chip, all of you in the audience probably, because you've seen a chip before, you imagine there's a chip kind of like, like this. The chip that John just described weighs 70 pounds. It consists of 35,000 parts. 8 of those parts came from TSMC. That one chip replaces a data center of old CPUs like this into one computer. The savings, because we compute so fast, the savings of that one computer is incredible, and yet it's the most expensive computer the world's ever seen. It's $250,000 per chip. We sell the world's first $250,000 chip. But the system that it replaced, the cables alone cost more than the chip, this H100. The cables of connecting all those old computers. That's the incredible thing that we did. We reinvented computing, and as a result, marginal cost of computing went to 0. That's what I just explained. We took this entire data center and we shrunk it into this one chip. Well, this one chip is really, really great at trying to figure out this form of computation that without getting weird on you guys, called deep learning. It's really good at this thing called AI. And so the way that this chip works, it works not just at the chip level, but it works at the chip level and the algorithm level and the data center level. It works together. It doesn't do all of its work by itself. It works as a team. And so you connect a whole bunch of these things together, and it works at, networking is part of it. And so when you look at one of our computers, it's a magnificent thing. Only computer engineers would think it's magnificent, but it's magnificent, okay? It weighs a lot, miles and miles of cables, hundreds of miles of cables. And the next one's soon coming is liquid cooled, and it's beautiful in a lot of ways, okay? And it computes at data center scales. And together, what's going to happen in the next 10 years, say, John, we'll increase the computational capability for deep learning by another 1,000,000 times. And what happens when you do that? Today, we kind of learn, and then we apply it. We go train, inference. We learn, and we apply it. In the future, we'll have continuous learning. We could decide whether whatever that continuous learning result it will be deployed into the world's applications or not, but the computer will watch videos and new text and from all the interactions that it's just continuously improving itself. The learning process and the training process and the inference process, the training process and the deployment process, application process will just become one. Well, that's exactly what we do. We don't have like between now and 7 o'clock in the morning, I'm going to be doing my learning, and then after that, I'll just be doing inference. You're learning and inferencing all the time. And that reinforcement learning loop will be continuous. And that reinforcement learning will be grounded with real world data that is being through interaction, as well as synthetically generated data that we're creating in real time. So this computer will be imagining all the time. Does that make sense? Just as when you're learning, you take pieces of information and you go from first principles, it should work like this, and then we do the simulation, the imagination in our brain, and that future imagined state, in a lot of ways, manifests itself to us as reality. And so your AI computer in the future will kind of do the same. It'll do synthetic data generation, it'll do reinforcement learning, it'll continue to be grounded by real world experiences, it'll imagine some things, it'll test it with real world experience, it'll be grounded by that, and that entire loop is just one giant loop. That's what happens when you can compute for a million times cheaper than today. And so as I'm saying this, notice what's at the core of it. When you can drive the marginal cost of computing down to zero, then there are many new ways of doing something you're willing to do. This is no different than I'm willing to go further places because the marginal cost of transportation has gone to zero. I can fly from here to New York relatively cheaply. If it would have taken a month, I'll probably never go. And so it's exactly the same in transportation and just about everything that we do. And so we're going to take the marginal cost of computing down to approximately zero. As a result, we'll do a lot more computation.
That causes me, as you probably know, there have been some recent stories that Nvidia will face more competition in the inference market than it has in the training market. But what you're saying is it's actually going to be one market, I think. Can you comment about, is there going to be a separate training chip market and inference chip market? Or it sounds like you're going to be continuously training and switching to inference, maybe within one chip. I don't know. Why don't you explain some more?
Well, today, whenever you prompt an AI, it could be ChatGPT, or it could be Copilot, or it could be if you're using a ServiceNow platform, if you're using Midjourney, using Firefly from Adobe. Whenever you're prompting, it's doing inference. Inference is so it's generating information for you. Whenever you do that, what's behind it, 100% of them, is NVIDIA's GPUs. And so NVIDIA's, most of the time you engage our platforms are when you're inferencing. And so 100% of the world's inferencing today is NVIDIA. Now, is inferencing hard or easy? A lot of people, the reason why people are picking on inference is when you look at training and you look at NVIDIA's system doing training, when you just look at it, you go, that looks too hard. I'm not going to go do that. I'm a chip company. That doesn't look like a chip. And so there's a natural, and you have to, in order for you to even prove that something works or not, you're $2 billion into it.
Yeah.
And you turn it on to realize it's not very effective, you're $2 billion and 2 years into it. The risk of exploring something new is too high for the customers, and so a lot of competitors tend to say, we're not into training, we're into inference. Inference is incredibly hard. Let's think about it for a second. The response time of inference has to be really high, but this is the easy part. That's the computer science part. The hard part of inference is the goal of somebody who's doing inference is to engage a lot more users, to apply that software to a large installed base. Inference is an installed base problem. This is no different than somebody who's writing an application on an iPhone. The reason why they do so is because iPhone has such a large installed base. Almost everyone has one. And so if you wrote an application for that phone, it's going to have the benefit of, it's going to be able to benefit everybody. Well, in the case of Nvidia, our accelerated computing platform is the only accelerated computing platform that's literally everywhere. And because we've been working on it for so long, if you wrote an application for inference, and you take that model and you deploy it on NVIDIA's architecture, it literally runs everywhere. And so you could touch everybody, you can enable, have greater impact. And so the problem with inference is actually installed base. And that takes enormous patience and years of success and dedication to architecture compatibility, so on and so forth.
You make completely state-of-the-art chips. Is it possible, though, that you'll face competition that claims to be good enough? Not as good as Nvidia, but good enough, and much cheaper. Is that a threat?
Well, first of all, competition, we have more competition than anyone on the planet has competition. Not only do we have competition from competitors, we have competition from our customers.
Yeah, that's true.
And I'm the only competitor to a customer, fully knowing they're about to design a chip to replace ours. And I show them not only what my current chip is, I show them what my next chip is, and I'll show them what my chip after that is. And the reason for that is because look, if you don't make an attempt at explaining why you're good at something, they'll never get a chance to buy your products. And so we're completely open book in working with just about everybody in the industry. And the reason for that, our advantage is several. Our advantage, what we're about is several things. Whereas you could build a chip to be good at one particular algorithm, remember, computing is more than even transformers. There's this idea called transformers. There's a whole bunch of species of transformers, and there are new transformers being invented as we speak. And the number of different types of software is really quite rich. And the reason for that is because software engineers love to create new things, innovation. And we want that. What NVIDIA is good at is that our architecture, not only does it accelerate algorithms, it's programmable, meaning that you can use it for, we're the only accelerator for SQL. SQL came about in the 1960s, IBM, 1970s, in storage computing. I mean, SQL structured data is as important as it gets. 300 zettabytes of data being created, every couple of years. Most of it is in SQL, structured databases. And so we can accelerate that. We can accelerate quantum physics. We can accelerate Schrödinger's equations. We can accelerate just about fluids, particles, lots and lots of code. And so what NVIDIA is good at is the general field of accelerated computing. One of them is generative AI. And so for a data center that wants to have a lot of customers, some of it in financial services, some of it in manufacturing, so on and so forth, in the world of computing, we're a great standard. We're in every single cloud, we're in every single computer company, and so our company's architecture has become a standard, if you will, after some 30 some odd years. And so that's really our advantage. If a customer can do something specifically that's more cost effective, quite frankly, I'm even surprised by that. And the reason for that is this. Remember, our chip is only part. Think of when you see computers these days, it's not a computer like a laptop, it's a computer as a data center. And you have to operate it. And so people who buy and sell chips think about the price of chips. People who operate data centers think about the cost of operations. Our time to deployment, our performance, our utilization, our flexibility across all these different applications, in total, allows our operations cost, they call it total cost of operations, TCO. Our TCO is so good that even when the competitors' chips are free, it's not cheap enough. And that is our goal, to add so much value that the alternative is not about cost. And so we, of course that takes a lot of hard work, and we have to keep innovating and things like that, and we don't take anything for granted. But we have a lot of competitors. Yeah.
As you know, but maybe not everybody in the audience knows, there's this term artificial general intelligence, which basically...
I was hoping not to sound competitive, but John asked a question that kind of triggered a competitive gene. And I came across, I want to apologize. I came across, if you will, a little competitive.